Welcome to Ask and Learn.
Okay, well, in this problem, we have an ideal Otto cycle, and we have to repeat the problem 33 using specific heats at room temperature. So what the problem 33 wants is in part A, we have this ideal Otto cycle, and in part A, we have to find what is the temperature in point 3 and the pressure on point 3. Well, and how are we going to discover this? We have to remember the first thing we must do in this problem is remember that the first transformation in an Otto cycle is 0.12, is an isentropic compression. So this is the first transformation in the Otto cycle. And since this is an isentropic compression, we can use the relations of the temperature. So the temperature 2 can be described just as temperature 1. It multiplies V1, V2 to the power k minus 1. And that's going to be equal 300, which is the temperature 1. V1, V2 is the compression ratio, so 8 to the power of 0.4. And that gives us a temperature 2 of 689 Kelvin. And using the ideal gas law, we can use P2 equals V1, V2, T2, T1, P1. And well, this is going to be equal 8 that multiplies 689 divided by 300 that multiplies 95, which is the pressure, the initial pressure. And the pressure on point 2 is just 1745 kilopascal. Well, now that we have the informations about point 2, we can look to the transformation 2, 3, which is a transformation with constant volume. And in this transformation, we can use simply the input heat that enters the cycle, which can be described by the change in the internal energy. So this is just CV T3 minus T2 because it's a room temperature, this problem. Therefore, we have the input heat, which is equal 750 equals 0.718 is the CV that multiplies T3 minus 689. And from this, we get that the temperature 3 is 1734 Kelvin. So this is the first answer. Now let's look to the pressure. Well, the pressure we can take from the ideal gas law again. P3 equals T3, T2, P2, and this is going to be equal 4392 kilopascal. So that's the answer for part A. Let's move on for part B right now. So in part B, what we want is the network. And how are we going to find the network? Well, we know that the network is just the change in the energy. So it's the heat input minus the heat output. And the problem is we do not have the heat output. So let's calculate who is K out first. So this is just U4 minus U1, which is just CV T4 minus T1. Well, again, we have another problem here. We do not know what is the temperature for. So let's find out what is the temperature for first, and then we calculate the output heat. So then we can calculate the net work. And the temperature for we're going to take with the isentropic transformation T3 that multiplies V3, V4, K minus 1. So this is equal 1, 7, 3, 4, 1 divided by 8, which is the compression ratio, V3, V4, to the power of 0.4, and that gives us 755 Kelvin. And with this temperature, we can calculate the output heat, which is going to be 0.718 that multiplies 755 minus 300, which is equal 327 kilojoules per kilogram. Okay? And finally, the net work is going to be 750, which is the heat input, minus 327, which gives us a total of 423 kilojoules per kilogram. This is part B, and we still have to find the answers for part C and D. So part C. In part C, we want the thermal efficiency of the cycle. And the thermal efficiency is just the net work divided by the input heat. Therefore, we have 4 to 3 divided by 750, which is equal 56.4%. Okay, that is not good. Let's rewrite this. 56.4%. And finally, the item D, which is the mean effective pressure. And the mean effective pressure is just the net work divided by the change in the effective volume, V1, V2. So this is going to be equal, let me see, the net work divided by V1 that multiplies 1 minus 1 divided by R, which is the compression ratio. Therefore, we have 4 to 3 divided by 0.906 that multiplies 1 minus 1 divided by 8, and that gives us 534 kilopascal of mean effective pressure. And that's the final answer to this problem. Thanks for watching.